2 6 under root 2 plus log of 2 root 2 plus 2. Final answer. Okay, everything is clear up to now. This is question number 11 we have done. Now 12th question, 13th question, the two questions are left over. Let me take them now. Question number 12, what does it say? So question number 12 and 13, which are I think related to each other. Let me check whether they are related or not. I'm sorry. Now question number 12th question is question number 12. What 12th question is? What is the question 12? 12 is find the surface generated by the revolution of an arc of the catenary y equal to c cos hyperbolic x upon c about the axis of x. Okay, about the axis of x. Simple. This is the value. Catenary y equal to this about the axis of x. This we have done. Where we have done in 9th question, I think. Yeah. On the surface generated by the revolution of the curve. This about the x-axis between the okay, that was the between planes. Now 10th question, but on the surface of the solid generated by revolving an arc of the okay, this was something else. Okay, no problem. Let me do it afresh. Question number 12 is 12 question. Catenary is y equal to c into cos hyperbolic x upon c here. Is it same or a? C. Y equal to c cos hyperbolic x upon c. About the x-axis of x. Okay. So, an arc. Find the surface generated by the revolution of an arc of the catenary y equal to c cos hyperbolic x upon c. About the x-axis of x. Now, no limits are given, so we can take 0 to x. No problem. So that value is there. So this is area we have to find out about one arc of this catenary. About the x-axis, so 0 to x we will take. This is generalized question. Surface generated by the revolution of an arc of the catenary y equal to c cos hyperbolic x upon c. Okay, about the axis of x. Okay, so this is here about the axis of x. So area of the surface. Area of the surface we have to find here. What we have to find? Area of the surface generated by revolving an arc of this about x-axis. About x-axis. Now no limits are given, so we can take 0 to x. General question from the vertex to the any point. Okay, as given from vertex. Okay, 10th question by the surface of the solid generated by revolving an arc with one end at the vertex of the catenary about the x-axis. So the same type of question. 10th type of question is this. There it was a, I think. Yeah, a cos hyperbolic x upon a. Here it is c cos hyperbolic x upon c. Okay, that's the only difference. Now let me find out solution. So area of the catenary or of the surface. Area of the surface generated by revolving the arc of one. This is first equation of the curve of the catenary first. Area of the arc of the catenary 1 about x-axis. About axis of x, let me take axis of x is given by, this is simple question. The formula is twice pi into, it's about x-axis, so it is y into ds limits 0 to x we will take. Okay, so that is the point here. Now it can be taken as twice pi 0 to x limits. It's about y-axis, so it is about x-axis, so y into ds. It is y into ds upon dx into dx we will write. So we have to find out ds upon dx. So differentiating first with respect to x, we get dy upon dx is equal to, this is c into sine hyperbolic x upon c into 1 upon c. This is differentiation. We will multiply by coefficient of x upon c, which is 1 upon c here. So c cancel out. There is nothing but sine hyperbolic x upon c. Whatever coefficient of x is there, we will multiply by that coefficient in case of differentiation. In case of integration, we divide by that coefficient. If it was integration, then sine hyperbolic x upon c upon 1 upon c. But here it will be multiplied because it is differentiation. Okay, so this is sine hyperbolic x upon c only, dy upon dx. Therefore, ds upon dx, which is this equation 1 upon 1 plus dy dx whole square. So we have to find out this arc length, the derivative of arc length ds upon dx here. That will give us 1 plus, it is this value sine hyperbolic square x upon this square here. This is nothing but cos hyperbolic x upon c, because this will be 1 plus sine hyperbolic square is cos hyperbolic square x upon c. The square root and the square cancel out. This is cos hyperbolic x upon c, value of ds upon dx. Therefore, let me substitute here. This is twice pi. Therefore, area is equal to 0 to x here. Y is this value, which is c into cos hyperbolic x upon c. Okay. Now what about this? Into ds upon dx is this value. This is cos hyperbolic x upon c into dx. So what does it give us? Let me take now this here. So it will give us area. Let me rub this also. So we have to find out this area of the surface generated by revolving arc of this curve catenary about the axis of x. Now limits were not given, so 0 to x here. Generalize this. Therefore, area E equal to twice pi c. This c constant I have taken outside. 0 to x here. Now this is cos hyperbolic square x upon c into dx. This is same value, cos hyperbolic x upon c, cos hyperbolic x upon c. So this is the whole square of this. Okay, now this is, let me remove. Therefore, what the area here that we have to think about. So twice pi into c, 0 to x, integration of this. First, let me write this. Convert this by trigonometric identity. This value is nothing but 1 plus cos hyperbolic twice x upon c. This is twice x upon c. Angle twice of this. Divide by 2 into dx. 1.2 will come out. Is nothing but pi c only. Pi c. 0 to x. Now this is 1 plus cos hyperbolic twice x upon c here. Okay, this is the final value. Integration. It is pi c. Integration is x plus. It is sine hyperbolic. I'm sorry. It is sine hyperbolic twice x upon c upon 2 upon c here. So c will come here. C upon 2. Okay, so this is the value here. Final answer, limits 0 to x. Only at x some value will be there because at 0 both are zeros. Lower limit is not to be substituted. Final result of this is pi c into x plus 1.2 c into sine hyperbolic twice x upon c. This is the final answer because at 0 lower limit both will be 0. This is 0, sine 0 is 0, sine hyperbolic 0 is 0. That is 0. So only at x upper limit. This is the answer. Square unit, we can write it as square unit for a square unit, area, unit of area. Answer here. This is the same answer. This we have to remember. Why? Because this may be applied somewhere in 13th question. I have seen that for a catenary y equal to, now it is a cos hyperbolic x upon a. Only c is to be replaced by a here. This is a, this is a, this is a here. Pi a into x plus 1 upon c. The area of this 13th question is this. This is area here, capital S. Okay, so what does question number 13 say? Let me first read that what question 13 says, because this result is applicable there also. Let me check it. Now question 13 says, question 13 says that, what does it say? It says, for a catenary, let me take catenary y equal to a into cos hyperbolic x upon a. This is x upon a here. This is the only difference with 12 and 13. For a catenary y equal to a cos hyperbolic x upon a, here, x upon a, prove that. To prove, this is x upon a here. To prove here, now the proof is very important. What we have to prove here? The proof of this is, what is that? We have to prove that small a into capital S is equal to the volume of twice volume is equal to, okay, this is the, in the bracket I have written down, where a is equal to twice b is equal to pi into a, within a bracket it is a into x plus small s into y. That is the value here, small s into y here. Okay, now small s, that is the small s value. Small s is the length of the arc, while this capital S is where what is given to us, where s is capital, sorry, small s, this is the small s here, small s. Small s is the length of any arc from the vertex, okay, and capital S and V for volume are respectively the area of the curved surface and the volume of the solid obtained by the revolution of the arc about x-axis. Okay, here let me talk about them. Here what is S, capital S? S is the area of the curved surface, it says, generated by revolution of the arc small s about x-axis. It says about x-axis, yeah, axis of x, about x-axis. This is capital S here, this capital S. Try to understand. And V, the volume, this area we have to keep in mind. Okay, let me rub this. And what is the V volume? Volume is the, this is V is the volume here, volume of the solid generated by revolving an arc of this, by revolving the solid generated about x-axis, revolving about x-axis. The same thing here. This is the volume we will just calculate, and this is small s. This is small s. You write this small s here. Small s is the length of any arc, and small s here. Solution we are calculating. Small s is the, here small s is the length of any arc, of an arc, length of the arc, it says, length of any arc from the vertex to, from the vertex here, any arc from the vertex. That we have just taken s, small s here. Now this is the area. Now this area in this C only is to be replaced by A, because here the curve is A into cos hyperbolic x upon A. This is the same curve, same catenary type as we have taken in 12th question. So capital, this is the area here, curved surface is the same result here. we have from question 12 area of the surface generated by revolution of the arc or the surface about revolution of the surface about x-axis, revolution of the surface about x-axis is this. This is S here, capital S, area. But here we have to replace by S. Here in this question we have A in place of C. Only this is the difference. C we have to replace by A. Therefore, capital S in this case is pi into A. This is C here, so A we have to take. This is x plus A upon C, or sorry, A upon 2. This is 1.2 into A into sine hyperbolic twice x upon A. That is the angle of this sine. This is the value of S here. Now let me write this S. So we have S equal to this. We have capital S is equal to pi into A. So in bracket it is x plus 1.2 A into sine hyperbolic twice x upon A. This is the value. Okay, this is first equation. Now S, A into S, we will multiply this by A. So we will get here pi A square only. In the bracket, the same value is there. Twice B, the volume we have to find out first. What is the volume? With that we will calculate. But before that, now let me rub these 2 points here. This also let me remove. So we were having what is ds upon dx. Then watch ds upon dx. We had, what this is small s we have to find out. We had ds upon dx equal to, it was coming as cos hyperbolic. Was it sine hyperbolic, cos hyperbolic? It was coming as cos hyperbolic. Why? Because differentiation of cos is sine, but 1 plus sine square is cos hyperbolic. So this was cos hyperbolic x upon A in this case. Now integrating this, we have here, integrating it, we will get here ds equal to cos hyperbolic x upon A. Let me write here integration sign, this is dx here. On integration we get small s here, small s equal to, this is small s equal to cos hyperbolic sine hyperbolic x upon A, sine hyperbolic x upon A here. Now 1 upon A we have to divide, so it will be A here, A into sine hyperbolic x upon, this is value of s. If I substitute this s here, which is A into sine hyperbolic x upon A, and y is also to be substituted. So this value twice b. Let me first find out this s is this value. The small s we have just calculated, plus constant we are not taking here for this definite integral, limits 0 to x or something. Let me write here, this is small s. So small s we have A into sine hyperbolic x upon A. Small s we will substitute here, y also we have to substitute here. That is ya cos hyperbolic x upon A. Let me substitute that value. First of all, this value, which is twice b, we will prove that this value equal to this one. Therefore, pi into A into x. If I take this A outside, let me first substitute. Small s is this value. This in this equation I am substituting. Therefore, okay, let me first write same value. This is small s into y will give us pi into a into x plus s is this value. This is a into sine hyperbolic x upon a into y. Y is this value, which is a into cos hyperbolic x upon a. If I multiply this by twice and divide by 2, no problem at all. So that will give us twice sine a cos a. That means sine hyperbolic twice of that. It is pi into a. It is a into x plus a square now. A into a square. I have to divide it by 2 and multiply by 2. It is 2 into sine hyperbolic x upon a into cos hyperbolic x upon a. What is this value? This is pi a into x plus a square upon 2. Okay, this 2 sine a cos a. This is sine hyperbolic twice x upon a, twice of this value. If I take a common outside, so it will be pi a square. This is x plus 1 upon 2a into sine hyperbolic twice x upon a. Angle is twice x upon a now. Okay, so this is this value pi a into ax plus sy, which is equal to this value, which is pi a square into x plus 1.2a into sine hyperbolic twice x upon a. This is value sine hyperbolic 1.2a sine hyperbolic x upon a. If I multiply this as, therefore a into s, capital S, I am multiplying by a here, will give us pi into a square only. The bracket is the same value, x plus 1.2a into sine hyperbolic twice x upon a, which is this value. So as equal to this proved. But this pi a ax plus sy, we have proved that this is equal to this value, which is value of ax. This is nothing but equal to a into s, capital A into s, this value. Same value is obtained. So here we see that this is value of this pi a into ax plus s into y. This is small s into y, which is the same value we have obtained. This is this. Okay, so as is proved that as equal to this. Now twice b also we have to prove. Now let me find out what is twice b here. Now volume, we know that what is volume. Volume of the solid generated by revolving the curve or revolving the solid generated, let me write solid generated by revolving generated by revolving the curve, solid generated by revolving the curve about x-axis, is given by what? We knew that this was nothing but, in this case it was pi into y square into dx. That was pi into y square into dx here. So for this value, this is v is equal to, we are calculating v here, pi into y square into dx. Now 0 to x, we are taking the same limits as we took in that case. 0 to x limits are there. Okay, so this is pi, let me take outside, 0 to x, y square is this value, which is nothing but a square into cos hyperbolic square x upon a into dx. Now it is to be into pi a square, we have taken outside. Let me take that outside. That means v is equal to pi into a square, we have taken outside. This is y square value, a square into this. So cos hyperbolic square 0 to x here. Cos hyperbolic square x upon a is nothing but 1 plus cos hyperbolic twice x upon a upon 2. okay, into ds. This is the value here, and let me integrate this. Therefore, in this 1.2, let me take outside. This is pi a square upon 2. Integration of this is nothing but x plus these 2 I have taken outside. This is cos hyperbolic. This will be sine hyperbolic twice x upon a divided by 2 upon a. That means a upon 2. In the same value we have obtained. 0 to x limits are there. Limits are same value will be obtained because at 0 both are zeros. It is nothing but pi a square upon 2 into x plus 1.2a into sine hyperbolic twice x upon a. This is the same value which we have obtained. Now 2, if I take to this side, it will be twice v, 2 multiplied to this side. It will be pi into a square, within bracket it is x plus 1.2a into sine hyperbolic twice x upon a. The same value we have obtained here. Twice v equal to pi a square. This is pi a square x plus 1.2a sine hyperbolic twice x upon a. Okay, so twice v is also equal to the same value. As is also equal to the same value. And this pi a into ax plus s by e, small s is arc of length of the arc. So this value is also equal to the same. That means as equal to twice b equal to this, hence proved. Twice b is this, is twice b. As is the same value, pi a square x plus 1.2a sine hyperbolic twice x upon a. This is also x plus pi a square x plus 1.2a sine hyperbolic x twice x upon a. And this was also obtained the same. This value, when I solve, obtained the same value. This is what we have proved. Hence, this is the same result. Hence, we can say that all the 3 values are equal. That means this is proved. Let me now say here, hence, all the 3 results are same. Therefore, A into capital S equal to twice into V volume here. This is S is surface, area of the surface here, area of the surface is equal to pi into A, within bracket it is A into S plus small s into y. Y is this value. Small s is the length of the arc, which I just calculated from ds upon dx. We were having what? Cos hyperbolic x upon a. I integrated this, then we obtained the same value. ds upon dx was this value. Okay, so from this we obtained s equal to. Then I substitute this sine hyperbolic x upon a or a into this. We substitute. Then y also we substitute. Then we solve it. So this is what this small s is this. This small s is from this length of the arc differentiation. We integrated this, we got s here. So then substituted this s. Y also we substituted from first equation. The first equation. Okay, so all the results are same. Hence proved. This is proved. Hence proved. All the 3 results are same. Question number 13 is also proved. Okay, so this ends this topic here. I mean, for Cartesian equations or Cartesian coordinates. This is area of surfaces of revolution. Area of surfaces of revolution for Cartesian equations. Okay. Next topic is, I'll take the same topic but for parametric equations, then for polar equations next, and after that 4th exercise will be about that is, I think, double integration of something. Okay, or length of the okay, that surface area of the surface about any line, not about axis but about any line, which we have discussed out already in the beginning, in the definition part of this, the beginning of this topic. So from there we have now obtained 4 topics I discussed about for Cartesian coordinates, for parametric equations, then for polar equations, and when the curve area of the curve is obtained by revolving the arc, length of the arc or the surface about any line about any straight line other than the axis. That was the fourth topic. All these 4 topics we have discussed about, and these questions are taken only for Cartesian coordinates. Next time I'll take for parametric equations or parametric coordinates. Okay, so that is the next topic of ours. Okay then, see you in the next lecture series. I'm sorry.